Hi, my name is Jérôme Vieilledent. I am a developer advocate at Blackfire.io.
Hi, my name is Sümer and I work as a senior software engineer at Blackfire.io.
Today, I'll be showing you ways to make your applications incredibly fast. Performance optimization is quite often a hard topic, as you may not know where to look and where to begin with. That's the point. You cannot optimize something you don't see or measure, so we will need to collect and organize data for that very purpose. It sounds overwhelming, and it is somehow. So, we're going to use a tool specifically designed for this, and that will do all the hard work for us so that we can focus on what matters, writing simple and efficient code and making the world a beautiful place.
This specific tool is called Profiler. So profilers can be categorized into two types, tracing and sampling profilers. Tracing profilers provide detailed information and accurate data about the behavior of an application. They hook into specific events and operate precise measurements under the hood with a cost of an overhead. For example, function tracing profilers operates measurements whenever a function call or exit happens, while a line tracing profiler would work on every line being executed. Sampling profilers, on the other hand, took another approach and they sample the application at regular intervals and aggregates this information, lowering the impact of the implied overhead. Profilers definitely measure time, but when it comes to computing, there are different flavors of time. Wall time, CPU time, and I/O time. We will be walking over each one of them later in this presentation. Another important metric that can be measured is memory. Memory consumption of a function makes sense for debugging some performance-related issues as well. So let's walk over a few profilers in the Python ecosystem as an example that have unique feature sets. So the first one will be the line profiler. Line profiler measures per line wall time, and you can inspect its output from the command line. Yappy is another profiler which measures per function wall and CPU time. It can profile multi-threaded applications as well as async IO and Gevent applications. And you can see per thread traces from its output. And you can use key cache grind to visualize its output. The PySpy is a sampling profiler and it has a top-like CLI. It measures per function CPU time. You can output as flame graph or speed scope formats. And it can also show GIL contention if possible when there is a multi-threaded application. Monologue is a memory profiler that's included in the standard library since 3.4. It basically what it does is it traces all malloc, realloc, and free calls and saves a traceback along with the allocation. Thus, you can trace C extension allocations as well, and you can see the memory consumption of each these allocations. Blackfire measures per function wall, CPU, and I/O time and memory simultaneously. It's enabled only on demand, thus have zero overhead when the profile is not used. It has a web UI to show its output as call graph and timeline. And timeline is pretty similar to flame graph. So let's dive in a little bit more on how Blackfire works.
So, let's say you've already opened a free account on Blackfire.io and installed Blackfire on your computer. Well, the installation is widely covered in the documentation. But before we jump in profiling of our code, I want you to understand just a little bit about how this all works. Well, let's jump to the documentation and let's look for Blackfire stack. Here it is. Whoa, the diagram that shows you exactly how Blackfire works appears. Let's zoom in a bit here. All right, there are actually three things that we need to install. The first, which appears here in the middle, is called the probe, which is really just a pip package. You'll install it in your project wherever your code is running. I mean, like your local machine and later on production. The probe's job is simple but huge. It's responsible for collecting all of the information. It means all the function calls, how long each took, which function called which other function, how much memory did something take, network request. Well, you get the idea. And by the way, the process of collecting all the data is sometimes called instrumentation, which I only mention so that if you see these fancy words, it hopefully won't confuse you. The second thing we need to install is called the agent. This is a service or daemon that runs on your computer, well, within a container or on your production machine. It just sits there and waits. And when the probe is finished with collecting all the measures, it sends them to the agent. And the agent does some processing on it, like removing unimportant information and anonymizing things, then ultimately send the data to the Blackfire servers. It's somehow the middleman. So basically, the probe and the agent work together to collect the info and send it to Blackfire. The last piece you need to install is a browser extension, which is sometimes called the companion. Remember, the probe is not profiling every single request. It's always on demand. Normally, when a request comes in, the probe, well, yawns and does nothing. The browser extension's job is to actually activate profiling. It basically says, hey probe, wake up. I'm going to make a request and I actually want you to do your thing. You know, collect all the measures, etc. and send them to the agent. Cool? Well, text me when it's done. And that's it. This bottleneck fighting superhero trio is our ticket to performance glory. Well, next, let's see what they can actually do for us. All right, let's boot up a server to discover our application. But first, let's dive into our virtual environment for this. So I'm using pip is, so I'm gonna use the shell command. All right, we're set to go. Well, for running a server here, instead of using the Python binary from my virtual environment, I'm going to use Blackfire Python. This command is actually a wrapper around your Python binary, which ensures that everything is set as expected. Well, it mainly instantiates the probe and asks it to wait for being asked a profile. So I'm going to do this now. Blackfire Python manage.py, I'm using Django applications here, run server. All right, it seems that we're good to go. Let's copy this now and jump into the browser. Right, now you understand how important this project is. The world has been looking for the Bigfoot or Sasquatch for years. And thanks to the Bigfoot fanatic community on our site, Sasquatch sightings, we are closer than ever. In our case, better performance doesn't mean more profit, it means more Bigfoots. Do I know where the performance problems are? Nope, no idea. And honestly, I was too focused on getting the site to production to obsess over performance. That might not be the best idea, but still. Let's use Blackfire to find the bottlenecks, if any, to Sasquash them. So, we're ready to profile. But where should we start? Well, let's just click on the view details about a Bigfoot sighting. And all of this data comes from some data fixtures that we use to pre-populate the database while setting up the project. It uses a bunch of random data up here, and each sighting has a bunch of random comments. When we loaded the page a second ago, please note that the Blackfire probe did absolutely nothing. Because to activate it, you need to click on the browser extension, which I installed here. Oh ho, moment of truth. Let's click here. Well, there it goes. it goes from 0 to 100%, and as it actually makes 10 requests and averages their data. We can also give this profile a name to keep our account organized. Well, let's say show initial citing page. There we go. Now, well, in this top bar, we can also see the profile summary with the different dimensions on the profile. So here, the wall time, the IO time, the CPU time, the memory, external HTTP requests, and database interactions. We'll go into details a bit later. Now just click on the View Call Graph button to go to a URL on their site, on the Blackfire website. Hello to our profile. Well, next, let's start diving into this mountain of information and see how we can use it to find hidden hidden performance bug. Yes, I know. The cool looking graph in the middle is calling to us. But let's start by looking at the left side. The list of function calls ordered from the functions that took the longest to execute on the top down to the quickest on the bottom. Well, actually, Blackfire prunes or removes function calls that took very little time, so you won't see everything here. The functions are ordered by time by default because we are viewing the call graph in the time dimension. You can also look at all of this information ordered by several other dimensions, like functions took the most memory. It's kind of like the process manager on your computer. You can see which applications are currently taking most CPU, most memory, reading most info from your disk, or even using the most network. But more on these dimensions later. In the profiling world, time is called wall time, but it's nothing fancy. Wall time is the difference between the time at which a function was entered and the time at which the function was left. So wall time is a fancy word for time, the amount of time a function took to run. So we just find the function with the highest wall time and we just want to find it and optimize it, right? Well, what if a function is taking a really long time, but actually 99% of that time is due to a function that it calls itself? In that case, the other function might be the problem. To help sort this all out, wall time is divided into two parts, exclusive and inclusive time. So if you hover the red graph here, you'll see this. Exclusive time 65.2 milliseconds, inclusive time 158 milliseconds. Inclusive time is the full time it took for the function to execute. Exclusive time is more interesting. It's the time a function took to execute excluding the time spent inside other functions it called. It's a pure measurement of the time that the code inside this very function took. Well, right now, we're actually ordering this list by exclusive time because that usually shows you the biggest problems. Well, you can also order by inclusive time, which is probably not very useful here. The top item is where our script starts executing, and second in the next function call, and so on. So, well, back to exclusive. So, apparently, the biggest problem, according to exclusive time, is the initializer of the Django DB models base citing class. Right, this matching one of my model classes. And before we dive further into the root cause behind this slow function, the other way to order the calls is by the number of times each is called. So let's click here to change this order. And apparently the function that's called the most time, almost 7,000 times, is built-ins.setAutre. I wonder who calls that. Oh, and I can also notice that, that citing initializer is also quite high on the list based on the number of calls. Could this be related? Well, first let's click to expand the setArt function. Even though we're viewing the call graph in the time dimension, this gives us all the information about this function: the wall time, the I/O time, the CPU time, and even the memory. Well, this isn't seem to be a particularly time-consuming function. Well, all is relative, of course, but its exclusive wall time is around 26 milliseconds. Compared to the whole wall time, it looks quite minimal. And wall time itself is broken into two pieces. And this is actually important. We have the I/O time and the CPU time. There is nothing else. Either a function is using CPU or it's doing I/O operation, like talking to the file systems or making network calls. Well, it seems to be broken into two parts, but most of the time seems to be spent in the CPU time. Okay, but who actually calls this function so many times? Above this, see those down arrow buttons? These represent the three other functions that call this one. The size is relative to how many times each one calls this. Let's click the first one. Aha! It's our citing model initializer. So that's the function with the highest exclusive time, and it calls this function 6,812 times. So it's definitely a problem. Well, and if I click the two other arrows, you can see that the other colors. One call is, well, for 27 times from Django models as well. And the other one, which is less than once, and it's less than once probably because, the probe averages the 10 different requests it made in the beginning. All right, let's close this up and go back to ordering by the highest exclusive time. Here we go. All right. Let's open up citing init. And as I mentioned, even though we are currently viewing the call graph in the time dimension, we can see all these functions dimensions here. Hover the time graph. Okay, even though the exclusive time is significant, well, most of this function's time is still inclusive, right? It's taking up by other functions that it calls. That may give us a hint as to if the problem is inside this function or is inside something it calls. But remember that the second, the function it calls just after, which can be appeared here by clicking this button, is a built-in function. So, and it's taking quite a lot of time here, 88 milliseconds at overall. So actually every dimension has an inclusive and exclusive measurement. So back here in the dunder init function, so we can observe the exclusive and inclusive dimensions for input output and CPU. That's also memory. That's also very interesting. All right. What I really want to know though is what's happening in our code to cause this function citing dunder init be called so many times. So to figure this out, let's click on the biggest arrow above. Aha! It's our Bigfoot models comment dunder init, which seems to be the main culprit. But honestly, I'm not sure how these two functions interact together. So next, let's use the call graph, this pretty diagram on the right, to get a full picture of what's happening and how to fix it. There are two different ways to optimize any function. Either optimize the code inside that function, or you can try to call the function less times. In our case, we found that the most problematic function is Django DB models based citing dunder init dunder function. But while it is based on one of our model classes, the process of creating its instances is specific to Django models. So it's probably not something that we can optimize. And honestly, it's probably already super optimized anyways. However, we could try to call it less times if we can understand what in our app is causing so many calls. Well, the call graph, the big diagram in the center of this page, holds the answer. Let's start by clicking on the magnifying glass next to citing init. That zoomed us straight to that node on the right. Let's zoom out a little. The first thing to notice is that the call graph is a visual representation of the information from the function list. On the left, it says this function has two colors. On the right, we can actually see those two colors. So when you're trying to figure out the big picture of what's going on, the call graph is always nicer. Well, let's zoom out a bunch further. Now we can see a clear red path that eventually leads to the dark red node down here. This is called the critical path. One of Blackfire's main jobs is to help us make sense out of all this data. One way it does that is by highlighting the path to the biggest problems in our app. Well, I'm going to hit this little home icon that will reset the call graph instead of centering it around citing init node. In this view, Blackfire hides some less important information around the node, but it gives us the best overall summary of what's going on. We can clearly see the critical path. The critical thing to understand here is, why is that path in our app so slow? Well, let's trace down to the problem node to find where our code starts. So let's first start with the main function. All right, so here is our view being rendered, right? Bigfoot.view citing show. Okay, then it calls render. It goes through the template engine. That's interesting. It means the problem is coming from inside a template. Okay, down further. Oh, it jumps into a Django template extension called user activity texts that calls Bigfoot models user get recent comments counts. And okay, and right, this is the last function before it jumps into Django models internals. So the problem in our code seems to be something around this user activity text stuff. Well, let's open up the citing show view. Let's open up the code. Okay, it's pretty straightforward. And it's rendering this citing show.html template. Okay, well, this is the body block. Let's find the user activity text, which is here. Okay, it's within a loop from the citing.commentset.all. Okay, if we look at the site itself, yeah, it's this. So if we look here, we can see that each commenter has a label next to them, like believer, hobbyist, or Bigfoot fanatic. Well, this label tells us how active they are in the great and noble quest of finding Bigfoot. Over in the template, well, we get this text via a custom filter. Well, this custom filter, the user activity text. Oh, let's open that up. Okay, so It counts how many recent comments this user has made. And via our complex and proprietary algorithm, it prints the correct label. Okay, back over in Blackfire, it told us that the last call before Django models was user.getRecentCommentsCount. There it is. Okay, let's open that up. Whoa! Okay, here's the story. But if you don't use Django models, you might not see the problem. But it's one that can easily happen no matter how you talk to a database. So yeah, each user on our site has a database relationship to the comment table. Every user can have many comments. The way our code is written, Django is querying for all the data for every comment that the user has ever made. Simply to loop over them and count how many we're creating within the last 3 months. It's a massively inefficient way to get a simple count. This is problem number 1. It seems obvious now that while I'm looking at it. But the nice thing is that it's not a huge deal that I did this wrong originally, because Blackfire points it out. Let's fix that performance bug. Okay, we gotta do a return comment. Oops. Return comment dot objects filter. And yeah, still filtering on owner ID, the self ID, and date added greater than, well, we already have datetime imported, dot datetime dot, well, starting from now, all right, minus datetime dot time delta, and well, let's say 3 months is, well, more or less 90 days, so 3 times 30. Okay, now that we have it, we just return the count. Alright, let's use this instead of my current crazy logic. If we've done a good job, we will hopefully be calling our model init function many less times. So let's profile and see the results. But first, let's see if I didn't make any mistake. Okay, it seems to work correctly. All right, it looks a little faster. So, well, in order to see what impact I could have, we're going to use Blackfire's comparison feature to prove that this change was actually good. We've just updated our code to make a count query instead of querying for all the comments for a user just to count them. So the patch would be definitely faster, right? Are we absolutely sure? Well, I think it is faster, but sometimes making one part of our code faster will make other parts slower. Fortunately, Blackfire has a special way to prove that a performance tweak does in fact help. So first, before seeing that, let's give this profile a name to stay organized. So show page after count query. All right, now let's go see the call graph. Hey, it's, well, 580 milliseconds. The last one was 754. So it is faster. We win. Well, yeah, I agree. It does look faster, but an important aspect of optimization is understanding why something is faster. Like, did it reduce CPU time, I/O wait time, and maybe more importantly, did this change cause anything to be worse? For example, a change might decrease CPU time but increase memory. And if that happens, well, would the change really be a good one? Well, it depends. Well, this leads me to one of my favorite tools in Blackfire, the ability to compare profiles. So let's click back to our dashboard. The two profiles on the top are from the initial profile, then the page after using the count query. On the right, we can hover these compare buttons. So, okay, click the first one. This was the original, and click the second one. And say hello to the comparison view. Everything that's faster or better is in blue. If anything that's slower or worse, it will be red. And yeah, it looks like the new profile is better in every single category. Good. And anyway, this comparison proves that this was a good change. Really, it's a big win. And on the call graph, the darkest blue, the critical path this time, is the path that improved the most. Now, let's look for the citing dunder init function that was causing all the pain. Well, it is the inclusive time is down by 150 milliseconds, and the memory even plummeted. But okay, right, wait a second. On the top, one of the items is called Sql Queries. Let's click on it. Oh, yeah. The total query time is less than before. Well, less by 1.2 milliseconds. That's negligible. But we removed 27 queries, but added 27 ones. Yeah, obviously we removed the big query, getting everything, and replace it by a simple count. Is that a problem? No, probably not. This change overall was good. And if having too many queries does create a real problem, not just an imaginary one of too many queries, Blackfire will help us discover that. The big takeaway here is don't just assume that a performance enhancement is actually better. Always compare and always reprofile. Okay, we fixed our first performance issue, but we should examine the new profile to check if we could improve it more. The function with the highest exclusive time now is this method execute of psychopg2 extensions cursor object. Well, which is a low-level function that executes Sql queries. These are taking almost 50 milliseconds and are being called 57 times. It more or less corresponds to the number of SQL calls that are being reported in the database dimension. And clicking on Blackfire Recommendations tab on the left shows what Blackfire is suggesting us. It clearly is saying that we are executing too many queries and that we're loading too many ORM entities. Let's click here to see. Yeah, it's basically telling us to reduce the number of SQL queries and how to do it. And the same for ORM entities, here mentioning the Django models objects we are loading. All right, it's not an ideal situation, but is it worth fixing? I guess it depends on how much you care. and whether the fix would be easy or if it would add a lot of complexity to our app. Okay. But when you're trying to identify where the problem is, there are two ways to look at the call graph. First, you can read from top to bottom like we did before. Trace through your whole application flow to figure out what's going on down the hot path. Or you can do the opposite. Start at the bottom, start where the problem is, and trace up, using the critical path again to find where your code starts. Well, here again, I'm going to start from the top. All right, the main function, and then we can see Django is booting up. It's loading all the middlewares, and then it renders our view, citing show view. This is, well, it renders then our template. This is really the same as before. And now down to, again, our user activity text called 27 times, which again calls user.getRecentCommentsCount. Right, that makes sense. 27 counts, 27 times, well, we probably have 27 comments on the page. And for each comment, we need to count all the author's comments to print out this label. Before we think about if and how we might fix this, let's back up and look at other dimensions to this profile. Let's have a look at I/O time. Yeah, we can now have a completely redrawn call graph only based on I/O time. We can do the same on CPU time, also using memory. Okay, when we look at this I/O time dimension, the psycopg2 execute function, the function that makes SQL calls, shows up here as well as a big problem. The point is, while wall time is typically the first dimension you're facing, don't forget about these other ones. They can give us more information about what's going on. Is a function slow because of inefficient code? Or is it, for example, because of a network call? Or is it some I/O problem? Maybe you have an issue with your SSD or your hard disk. As we already discovered, the problem is coming from the user.getCommand count. Get user command count that we had in the wall time view. Okay. Here, there, and there. Okay. Let's go into our code again. As we already discovered, the problem is getting from this function, which is called by the user activity text filter. Bigfoot extras, let's open it. As we already discovered, the problem is coming from user.getRecentComments.count, which is called from the user activity text filter. Each time we render a comment, getRecentCommentsCount is called from the user object attached to this comment. It happens that the same user can comment many times on the same citing, as well as on other ones. When that happens, we are making a query to count that user's comments and repeat the operation for each comment. That's wasteful. So here's one idea. Let's leverage caching. We'll keep track of the status string for each user and use that to avoid calculating the status more than once for a given user. Let's first enable the cache in our settings.py. All right. Here, activating the lock memcache backend here. Perfect. Now let's update user activity filter. Import django.core.cache import cache. Okay. And now let's update this to use the cache. Right. First, we define a cache key, which should be unique here per user ID. We then get the comments, the comment count from the cache, and if it's none, then we compute it and add it to the cache for 1 hour. That looks there. Okay, I just refreshed and reprofiled the page. This time, things look way better, but let's not trust it. Let's go compare the original profile to this new one. Okay. The changes are significant, and there doesn't seem to be any downsides to the changes we made. And the Sql Queries count dropped by 27, which was expected. And really, this is no surprise. Full caching things will, of course, be faster. But the good thing here is that the user activity text cache is now distributed. I mean, each user being able to comment on all citing pages, well, their activity text will be reused everywhere they're commenting. And yeah, I think that's quite a big win.
The most common mistake that is done during performance optimization is premature optimizations, as Nut states. We should be measuring our code, if possible, even in all development steps, from development to production. So using a tool for this very purpose is key. Although there are no common rules to fix all kinds of performance-related problems, here are some guidelines for debugging and fixing performance issues. So the first one is obviously measure, and always is better. Using a tool for this is key, like I said. The second one might be you should be focusing first on architecture, design, and algorithms rather than doing some language level micro optimizations. A simple performance problem can open you a new ways of refactoring your architecture or code base and make it even better than before. And during development, check if there is a standard library that function that accomplish what you are trying to do, or what is the best practice for your case. Although this might seem very simple, we as developers may waste time because of not checking the documentation properly or not looking for best practices of the framework. And if you really need performance at the end of the day, there are numerous tools for that. In Python world, you can, few examples might include like Cython, Numba, or directly write your code as a C extension.
During this workshop, I showed you how profiling with Blackfire can be useful to track down performance issues. You learned how functions are interacting with each other, how Blackfire provides recommendations based on the behavior of the application, how to read a call graph and to use the critical path, how to check the different dimensions of your application, input-output, CPU, memory, database calls, and how to compare profiles to visualize the impact of your changes. I hope you enjoyed this workshop as much as I did. Happy profiling, and feel free to ask any question. Bye bye.